Okay, imagine this. A robot that can learn pretty complex skills like manipulation or navigating new places, basically just by watching videos, like we learn.
Yeah, without needing perfect, step-by-step instructions or tons of specific training data for every single robot body it might use.
Exactly. Like, picture a robot arm watching a cooking show online, and then, boom, it can chop vegetables. Or maybe a drone watching a YouTube tutorial on warehouse navigation and figuring out how to map a new space.
That's really the exciting leap proposed in the research paper we're digging into today.
This work is definitely pushing towards, well, truly generalist robot policies, systems that aren't just stuck doing one job with one body.
The paper's called Learning to Act Anywhere with Task-centric Latent Actions. It's from researchers at the University of Hong Kong, Open Drive Lab, and Agibot.
And the core problem they're tackling is honestly a huge one in robotics, just the sheer variety of everything. Robots, environments, tasks.
Right. Every robot is physically different joints, different movements. It's what they call different embodiments. And usually, robot learning needs tons of data collected just for that robot doing that task.
Often with really precise ground truth action labels, too, telling it exactly what motor command to use when.
And that's the real bottleneck, isn't it? The internet is swimming in video data. People doing stuff, other robots doing stuff, but none of it has those clean, specific labels for your robot.
So using all that messy in the wild data is super hard because the action spaces are so different. What a human hand does isn't easily translated to a robot gripper.
Exactly. Knowledge transfer is the big challenge.
So their solution, which they call Univila, that's Unified Vision Language Action Model, tries to get around this. They propose learning in what they call a task-centric latent action space.
Think of it like a universal action language.
Okay.
It describes what needs to happen to get the task done, not the nitty-gritty details of how a specific robot achieves it.
Okay, so what are the key ideas behind Univila?
Well, first, and this is big, it learns from unlabeled video. That unlocks all that internet data. Second, it figures out how to separate the important task actions from, visual clutter or background movement.
And it compresses this understanding into a compact, discrete, latent space, like action tokens.
Exactly, which makes the whole learning process way more efficient and faster.
And the results seem pretty strong.
Yeah, they're showing state-of-the-art performance on standard benchmarks for both manipulation, like Libero, and navigation, like R2R. Plus, good generalization on a real robot.
So this could be a major step towards robots that learn skills more like us just by watching. Imagine robots learning from YouTube.
It really points toward that possibility. Less bespoke training, more general learning.
Welcome back to AI Paper Podcasts. We're the place you come to get up to speed on the latest important research in AI and tech.
Today, we're unpacking Univila. It's tackling that fundamental robotics problem. How do you build one AI that can control different robots for different tasks in different places and learn from messy real-world video?
So the core idea is to move beyond robot-specific commands, right? To learn a kind of universal action representation.
Precisely. It focuses on the outcome, the change needed in the environment for the task, abstracting away the specific joint wiggles.
All right, let's get into the details. We'll explore how they build this task-centric action space, the architecture they use, and look closely at those results on benchmarks and real robots.
Okay, so let's revisit that core problem Univila tackles. We mentioned traditional policies needing ground truth action labels.
Right, like for this robot arm to pick up that block, you need data showing the exact joint angles or end effector path for that specific arm.
And that's the immediate hurdle. Two different robot arms, even similar ones, have different control spaces. What works for one is often useless for the other.
And forget about learning easily from human videos. Our action space is totally different, so transferring knowledge, really tough.
Plus, all that easily available data, like online videos, is unusable because it lacks those labels. And it's messy, different cameras, moving backgrounds, things getting blocked from view.
Most existing vision language action models, or VLAs, they need supervised training on carefully curated, labeled data sets, which are expensive and just don't scale well.
People have tried other things, sure. Manually aligning action spaces, using fancy transformers.
Yeah.
But many still need tons of specific data or aren't robust enough for truly unlabeled web video.
This is where Univila's three-step method comes in. It sounds like this is the real technical core.
It really is. Step one is all about learning those abstract latent actions. And crucially, they do it unsupervised. No need for explicit control labels.
Okay, how do they manage that? Learning actions without action labels sounds tricky.
They use a clever setup with dynamics models. First, an inverse dynamics model, the IDM. It looks at a frame, say aught, and a future frame, aught plus k, and tries to guess the action that must have happened in between.
Okay, so inferring the action from the state change.
Exactly. Then they have a forward dynamics model, FDM. This takes the first frame aught and the inferred action at and tries to predict what that future frame aught plus k should look like.
Sort of closing the loop. Predicts action, then predict outcome from action.
But here's the twist. They don't just learn any continuous action. They use latent quantization, inspired by VQ-VAEs.
So they force the inferred action into a discrete codebook, like choosing from a limited vocabulary of action words.
Precisely. They snap the inferred action representation to the nearest code in a predefined codebook. They actually use N4 of these discrete action tokens per step, representing maybe a second of activity.
And what's the benefit of that quantization?
It forces the model to find the most salient aspects of the action, filtering out minor irrelevant variations. It creates that compact, shared action language and makes it robust to noise.
Okay, and what are they predicting with the forward dynamics model? Not raw pixels, you said.
Right, that's another key insight. Predicting pixels is brittle, very sensitive to lighting, textures, small shifts. Instead, they predict DynoV2 spatial patch features.
DynoV2, those are known for capturing more semantic information, right? Like object presence and spatial relationships.
Exactly. So by predicting DynoV2 features, the model learns latent actions that correspond to meaningful semantic changes. Object moved left, gripper closed, rather than just pixel changes. It handles the visual noise of web data much better.
Got it. Now, the paper mentions using language in this first stage to help decouple things. That sounded a bit complex.
It is a bit subtle, and the paper splits it across stages. But the core idea in this initial learning is using language instructions during this unsupervised training.
How does language help if there are no action labels?
Well, by feeding the model a task instruction, like pick up the red block, alongside the video frames, OAT and aught plus k, they condition the decoder part of the model, the FDM, on the language.
Okay.
So the model has to predict the future state O plus k, given the current state out, the quantized latent action on, and the language instruction at. Because the language already provides the high-level task goal, the latent action ADDI gets pushed to represent only the necessary environmental changes or visual details needed to progress towards that goal, essentially factoring out the high-level task itself.
Ah, I see. So the language tells it what the goal is, forcing the latent action to encode the low-level how in terms of environmental change, separating it from visual noise or task-irrelevant motion.
You've got it. It helps guide the latent space to capture task-relevant dynamics, even without explicit action labels. The result is this universal, task-centric representation of environmental interaction. It's a clever way to use language supervision indirectly.
Okay, that makes more sense. So stage 1 learns this universal action vocabulary. What's step 2?
Step 2 is training the actual generalist policy. This is the brain that will use those learned latent actions.
So this policy takes the robot's current view and the task instruction and predicts a sequence of those latent action tokens.
Exactly. They use a powerful autoregressive transformer, specifically building on a pre-trained vision language model called Prismatic 7B. Input is visual features like DynoV2 or SIGLIP and the text instruction. Output is the sequence of latent action tokens from the vocabulary learned in step 1.
And because everything maps to this shared latent action space,
they can train this policy on a huge mix of data. Robot manipulation, human videos, navigation data, it all gets translated into the same action language, allowing for massive cross-domain knowledge transfer.
And you mentioned efficiency. Training in this compressed latent space must be way faster.
Dramatically faster. They report Univla pre-training took about 960 A100 hours. For comparison, OpenVLA, another large VLA model, took around 21,000 A100 hours. That's a huge difference.
Wow. Okay, so step 1 learns the actions, step 2 trains a policy to predict them.
Yeah.
What's step 3? Getting it onto a real robot.
Precisely. Step 3 is deployment, translating those abstract latent actions back into concrete motor commands for a specific robot.
How's that done? A separate model for each robot?
Kind of. They add lightweight robot-specific policy heads or decoders. These are small networks trained after the main policy. For each robot type, you train one of these decoders.
What does the decoder take as input?
It takes the predicted latent action token embeddings from the main policy, but also incorporates the current visual features from the robot sensors.
Why the visual features again?
It helps the decoder contextualize. The latent action might mean move forward, But how to move forward depends on the current scene, obstacles, terrain, etc. The visual input helps the decoder translate the abstract action into appropriate context-specific motor commands for that robot right now.
And these latent actions represent about a second of activity, you said.
Yeah, so the decoder naturally outputs action chunks, a short burst of control commands covering that interval. This also helps with real-time control.
And adapting to a new robot is efficient.
Very. You don't retrain the massive main policy, you just train a small decoder head for the new robot. They use parameter-efficient fine-tuning, or PET, specifically LoRa.
LoRa, right. That lets you adapt huge models by only tuning a tiny fraction of the parameters.
Exactly. The decoder head itself is small, maybe 12.6 million parameters, out of around 123 million total trainable parameters, including the head. Makes deployment much more practical.
Okay, and they have this neat trick using history, too, inspired by chain of thought.
Yeah, instead of feeding in lots of past video frames, which gets computationally heavy, they feed the history of predicted latent action tokens back into the policy's input prompt.
So the policy kind of sees its own recent plan.
Exactly. It provides temporal context, what it just decided to do in a very compact form. This helps it plan better for longer tasks or react to changes over time. Their results show this really boosts performance, especially on multi-step tasks.
All right, seems like a solid three-step process. How well does it actually work? Let's talk performance.
They tested it extensively, starting with manipulation tasks on the Labero benchmark.
Libero, that one tests lots of things, right? Spatial reasoning, generalizing to new objects, long sequences.
Yep. They compared Univila against strong baselines, LAPA, Octo, OpenVLA, others. Some also use latent actions or VLA models.
And how did Univili do?
It came out on top across the board. On the full data set, it hit a 95.2% average success rate. Compare that to OpenVLA at 76.5% or LAPA at 65.7%. That's a pretty significant improvement in reliability.
Wow, and what about generalization? That was the whole point, learning from diverse data.
That's where it gets really interesting. Even when Univili was pre-trained only on the Bridge V2 robot dataset, it got 92.5% success. But get this, pre-trained only on human video data from Ego 4D, it still achieved 81.7% success on the Labero robot tasks.
Wait, trained just on human videos, it beat other methods trained on robot data?
Often, yes. It outperformed baselines that had seen much more in-domain robot data. That really shows the power of learning that abstract, task-centric action space. It transfers knowledge remarkably well.
That's impressive. What about handling variations, like new objects or distractions?
They tested that too. Changing lighting, adding visual distractors, swapping objects like using a marker pen instead of a screwdriver. Univili significantly outperformed the others again. Its average success score was 68.9%, while LAPA got 28.9% and OpenVLA only 20.0%.
So it's much more robust to these kinds of real-world variations. Seems like the latent actions capture something fundamental about the task goal.
Exactly. Yeah. Shifting to navigation, they used the room-to-room benchmark, VLN-CE. It's language-guided navigation in realistic indoor scenes.
Follow instructions to reach a goal, basically. And Univili only uses a single RGB frame plus its history of latent actions.
Right, minimal visual input compared to some methods. And its Oracle success rate was 47.1%.
How does that compare?
Huge improvement over older methods like CTOSEC, 8.1%, or CMA, 10.8%, and even significantly better than OpenVLA, 17.5%.
Okay, but how does it stack up against state-of-the-art navigation agents?
It's comparable to Navid, which is a very strong baseline. But Navid needs the entire history of visual observations, making it much more computationally demanding. Univla gets similar performance with just the current frame and its compact latent action history. Big win for efficiency.
Efficiency really matters for real robots. Speaking of which, how did it do in the real world?
They deployed it on a Piper arm, a 7-do-off robot, and they gave it some properly challenging tasks.
Not just picking.
No, things requiring spatial awareness like store the screwdriver, tool use like clean the cutting board, handling deformable objects like full towel twice, and even semantic understanding like stack Hauer of Hanoi.
Okay, complex stuff. How did they measure success?
Both overall success rate and a stepwise score up to 3 points per task, rewarding progress on intermediate steps. Good for seeing if it gets stuck partway through.
And the results? Against things like Diffusion Policy, OpenVLA, LAPA.
Univili, trained on their full mixed dataset, got an 81.7% average success rate and a 2.63 average score. LAPA was way behind at 45% success, 1.95 score, and OpenVLA even lower at 38.3% success, 1.63 score. Univila was clearly the superior generalist policy in the real world.
What about compared to diffusion policy? That's usually strong on specific tasks.
Interesting comparison there. For something like towel folding, which needs a very precise trajectory, diffusion policy actually had a slightly higher success rate, 53.3%, Univila's 46.7%.
Ah, okay, so DP is better at rote execution.
For that specific task, yes. But Univila got a higher stepwise score, 2.47 versus 2.33, meaning it was better at completing the individual steps reliably, even if the final fold wasn't always perfect.
So Univili might be better at figuring out the sequence, even if the execution isn't quite as smooth as the specialist policy.
Seems like it. And for task meeting semantic understanding, like Tower of Hanoi, Univila blew DP away, 86.7% success versus just 6.7% for DP. The vision language grounding really helps Univila understand what to do.
And critically for real robots, what speed?
Univila runs at 10 Hz closed-loop control on an RTX 4090. They mentioned OpenVLA had noticeable latency, like 0.18 seconds per step causing stuttering. Univila's approach of planning in the compact latent space and decoding in chunks makes it fast enough for smooth real-time interaction.
That's crucial. So did they look deeper into what those latent actions actually represent?
They did. Qualitatively, they showed cool visualizations where that same latent action token leads to semantically similar behaviors across different robots and scenes. Like, one token consistently means pick something up, whether it's a Franca arm or a Widow X.
So it really is capturing a universal concept.
It seems so. They even showed alignment between actions learned from manipulation videos and navigation videos, suggesting it generalizes across domains.
And quantitatively, did they prove the task-centric part matters?
Yes, through Ablation Studies. They trained versions where the latent actions tried to capture all visual changes, not just task-relevant ones. Performance dropped significantly, especially when trained on noisy human videos like Ego 4D. Filtering out irrelevant stuff is key.
Makes sense. Did they check if the model is actually looking at the right things?
Yep, they visualized attention maps. The model focuses on the robot's end effector, the objects being manipulated, and relevant parts of the scene, while ignoring background clutter. It confirms the latent actions are spatially grounded and task relevant.
And does adding more diverse data actually help? That's the scalability promise.
They showed clear evidence for that, as they added more data types, Bridge V2 robot data, then OpenX manipulation and navigation data, then Ego 40 human data. The performance on downstream tasks, Lubro R2R, Real Robot, consistently improved.
So it scales. It can actually learn from mixing all these different sources.
The results strongly suggest it can. It reinforces the idea that learning from vast, heterogeneous web-scale video is a viable path forward.
Okay, and a couple more quick technical points. They did ablations on the decoder and the history mechanism too.
Right. They showed their action decoder, the one using visual features for context, works much better than simpler autoregressive decoding, especially on long tasks like liberal long, a 42.1% improvement. Vision helps resolve ambiguity.
And using the history of latent actions.
That also gave a significant boost, particularly on sequence-dependent tasks. R2R navigation improved by 16.5%, liberal long by 3.9%. This is a very compact way to add that crucial temporal context for planning.
Okay, let's try to wrap this up. What are the big takeaways from Univila?
I think the core contribution is definitely that task-centric latent action space. It's the key that unlocks learning from massive, unlabeled, diverse video datasets.
And the ability to decouple the important action information from visual noise and the specifics of the robot body seems absolutely critical for that to work.
Agreed. The overall architecture, the VLA transformer predicting latent tokens, the lightweight decoders for specific robots, plus the historical action context, it all comes together into an efficient and impressively generalizable system.
And the results speak for themselves. State-of-the-art on multiple benchmarks, solid real-world performance on complex tasks. It's compelling stuff.
No, it's not perfect. The paper mentions limitations, like the fixed size of that latent action codebook might not be optimal for all possible tasks or robots. Maybe something adaptive would be better.
And they focused on single-arm robots. Scaling to, say, dexterous hands or two arms working together would likely need a more complex action representation.
True, but it definitely pushes the conversation forward. Does this mean we're getting closer to robots that don't need painstaking training for every little thing?
It really feels like a step in that direction. Univla strongly suggests that learning from observation, from the kind of messy video data that's everywhere, is feasible. So here's something to think about. If robots can learn skills just by watching videos online, what does that unlock?
Yeah. What new applications become possible when a robot can just watch a tutorial and gain a new capability? Could we see truly adaptable robots in homes, factories, or exploration far sooner than we thought?
A very compelling thought.
Indeed.
Well, that's our analysis of the Univila paper. Thanks for tuning in to AI Paper Podcasts. Stay curious, and we'll catch you next time.